have the right kind of hunting skill or smell. Okay, you have to sort of know what is and what isn't possible, and where, the time is ripe to get in. I mean, again, I could go with the interferometry and say, of course, I mean, I grew up as a radio astronomer. In my thesis as a student, I used VLBI to look at water vapor masers and their motion. So I'm an interferometrist at heart. Still, it was clear until, about 15 years ago that interferometry in the infrared, forget it. Yeah, not at the kind of sensitivity. But now that's very different. What we are looking at here is sort of the central few arc seconds in the upper left of the galactic center. The upper left is sort of the best you can do with a 10-meter glass telescope in seeing limited conditions. So what do you see? You see some very bright, near dark stars. Okay, these objects are really very massive. Actually. So the adaptive optics then improves this image from the top left to the top right by about a factor of 20. Now you can see individual stars very clearly. Some of the brighter ones, of course, you can see the artifacts of the adaptive optics not being perfect. You see this sort of ringing there. Yeah. And then now in the center, all of a sudden, there it is. That's J star. That's the black hole, which also radiates. And that's this little square which you see is now what you see as a big square on the bottom.
Yeah.
Okay. And whoops, what do you see? Not only one object, but heck, 1, 2, 3, 4, 5, 6, or whatever. Yeah.
Wow.
And that, in fact, is what the breakthrough is. The breakthrough is the resolution and therefore the precision of measuring things very accurately. And you take several of these images over 3 months, and then you get the left, the bottom left. Okay, so red was in March, green is May, and blue is July. And wow, I mean, you look at that. I mean, there's very obviously one star which came extremely close, even closer than S2. Another one is sort of moving the other way, and there are a few more. Yeah, so it's that's really the key thing. And I would say the interferometry is a very serious contender now, in my view, for certain types of measurements one would like to do. If you think about these exoplanets, I mean, the problem is you have a planet, and then you have the much brighter central star. And the way usually this is dealt with is you basically
mask
the bright star, and then you look only at the planet. Well, with adaptive optics, that's fine, because then the star becomes relatively compact and you can actually see the planet. But the adaptive optics is not perfect. And the star is say a billion times, or certainly a million times brighter than the planet, and a little bit of this uncorrected light is then floating around near the planet and generates noise. So the noise is now not anymore instrumental, so to speak, but it's due to uncompensated light from the scattering from the star. The interferometry, on the other hand, doesn't do that, because the same effect in the adaptive optic systems on the individual telescopes which we're using also make not perfect correctors, but they're not correlated, and so the interferometer blends that out completely. So that's why all of a sudden currently the spectra which we're producing with gravity of exoplanets are the best in the world by a factor of 10. So if you take a time trace of that, then you would see it varying on typically timescales of 30 minutes or so, which, by the way, is the sort of orbital timescale of gas on the innermost stable orbit. Okay, so that's our interpretation. That's what you're seeing here. It's very, very hot, about 10 billion. 100 billion degrees or 100 billion degrees gas, which is doing synchronous radiation. So it's polarized, typically 10 to 30%. So in fact, by using wave plates, we can analyze the polarization of the emission. And what we find is that the polarization is highly aligned. And so with that technology, we can actually study magnetic fields in the vicinity of the black hole. Extremely exciting.
What is your philosophy? The students that you mentor, the postdocs, et cetera, what do you try to inculcate in them to have them fulfill their potential as a complete scientist?
Right. I mean, I would not have the audacity to say that I understand the theoretical work at the depth which is needed in the end to make reliable statements. Okay. So, for instance, if you want to investigate, the star cluster in the center and make a proposal how these stars would come about. That's sufficiently complicated, I would say, that I certainly wouldn't be able to do that. And so here's rule number one: is you have to have a team, and after all, that is what happens. It's not a single individual here; it's a substantial team, which in our case, of course, grew over time. Was initially largely based at MPE, but is now European. Okay, I mean the interferometry is really involves at this point about 100 people. So that's clearly not done anymore, even at a pretty well endowed Max Planck Institute. But it's the range of people in a team, so that you can talk to people about various things. We talked about interferometry. You can, in hindsight, you can see interferometry as an incredible amount of pioneering of a field, but you could also call it a failure because that he wouldn't get to the galactic center type sensitivities was clear after a fairly short period of time, and so this you have to bite the bullet. Sometimes you have to realize, okay, if you want to get there with this type of technique to get that kind of resolution, you will have to go into a different domain of work.